We might get a couple more people coming, but if not, that's fine. So let's go ahead and get started. So I guess I can make a couple opening comments. So I think at this point, work on miniKanren proper has been going on for something like 18 years. It's been a while now, or maybe 17 years that miniKanren has existed. Before that, there was Kanren. Before that, Dan Friedman had worked on logic programming largely in an educational context for many years. So, but for miniKanren itself, that language has existed for something like 17 or 18 years now. And it's changed over time. Now there are many versions of miniKanren and different types of logics that have been implemented. At the same time, I think we've only scratched the surface in terms of exploring this gigantic space. There are many, many types of logics we haven't tried implementing. From a software engineering standpoint, we don't have a modular single implementation of miniKanren that combines the different features or all sorts of things with type systems and formal verification and theorem proving and proof assistance and all other things that are close in spirit maybe to constraint logic programming we haven't really explored or have only explored a little bit. And there are also things like modern uses or integration with different types of AI technology, machine learning, neural networks, large language models, and so forth. It's been a little bit of work on that so far, such as the neural guided search paper at NeurIPS from 2018. But I think there's a whole lot more that could be done in any of these areas. We have one sort of really, really interesting example, I think, which is the relational interpreter and the idea that we can take an artifact, like a functional program, and by interpreting it in an interpreter that's written in a relational style, we can inherit this relational behavior. So that's something that seems to get people's attention. We can also do that with type inference, which Kisselhoff showed a long time ago, that if you have a type inferencer like this, you can also run it in a way to do type inhabitation and synthesis that way. And you can also do similar things with parsing. One of the big problems that we have in miniKanren and also in Prolog, and as far as I know, all general purpose logic and constraint logic programming languages have, is are conjunctions not actually commutative. We can say conjunctions commutative up to modulo, like modulo divergence versus failure when there is no answer you're asking for. And also in terms of performance differences, reordering conjuncts can have disastrous performance implications. So that's a very serious problem. There have been a number of people who have tried to explore that problem in miniKanren, also in Prolog and other logic and constraint programming domains. One approach is to restrict the language, do something like data log or answer set programming as a subset. But that's one of the problems. And then there's a whole range of research from various people in the miniKanren community as to try to make miniKanren faster with things like staged evaluation, supercompilation, trying to do static analysis, figuring out when a relation is primitive recursive, and do all sorts of tricks. We saw some discussions of that today, along with hand annotation and different types of performance tweaks that people have figured out. So there's a whole range of I should say, obvious things in the sense that they're continuations of things we've already been exploring to some extent. But it'd also be interesting to hear what are areas we haven't explored at all that maybe we should look into. And more broadly, miniKanren still isn't very well known. And can we articulate better what is interesting about this style of programming? Because it's weird. And one thing I found, and I found it during this conference, that I can't explain to someone what's compelling about miniKanren without giving them an hour-long demo. Okay, that was actually why I created Barliman initially, was so that I could show to a Java programmer what's interesting about miniKanren without spending like 3 hours explaining lambda calculus to them or something like that. So that I think is also an issue. We have 2 books, 2 editions of a book. We have various papers and theses and online and tutorials, but at the same time, we're far from having mainstream materials to teach people how to actually do this. And most people, even who know functional programming or logic programming, they maybe have heard of miniKanren, but they haven't used it, that sort of thing. So that's another thing I've thought about a lot. How do we teach people how to use this? How do we show them what's interesting? And what is interesting about miniKanren? Is it a one-trick pony? You can write a relational interpreter and that's it? Or is there sort of a grander vision of this? Okay, so those are just a few opening thoughts. I know people like Evan have a grander vision of what you could do with the system, or Greg have a grander vision of what you might be able to do with such a system. And I will say that there have been some real world use cases, such as the threat grid system in core logic, and at Precision Medicine Institute, called Precision Medicine Institute at University of Alabama, Birmingham. Greg and I and other people have been working on megaKanren. Greg's implemented dbKanren, which is a graph database system. In all these cases, we're using miniKanren or a variant of miniKanren, not exactly like Prolog, but more like Prolog or Datalog or things like that, in a more pragmatic way. So maybe in practice, there's going to be some mixture of pragmatic uses that are more like Datalog or answer set programming or things like that, and then also some this longer term project to try to make the relationality weird. It's already weird. To make it real, to make it more practical. Okay, so there's like this kind of long term vision. Oh, what if we could write everything as relations really? And then there's a shorter term thing like, well, what about having a practical tool more recently, and maybe have to use extra logical things like conde or conju, or use restricted versions of language for answer set programming or Datalog. So, okay. So those are a few things to think about, but I'd like to open it up to discussion, either people online through the Discord channel or people in the room, some of whom have all sorts of logic programming and functional programming experience. Actually, I think everyone in this room does. Does anyone have anything that they would like to share or ask questions about or think about for future of miniKanren relational programming?
Some questions. So I have a few questions. First,
can you give your name?
Yeah, my name is Yafei.
Okay.
So
Good idea. Yeah. So if you're gonna say something, please come up front.
okay.
The camera for the live stream, hello, is up there, and also this will be recorded for posterity on YouTube. So
Okay.
Yeah.
That. So my question about this. So my first question is, because miniKanren, its core its idea, its implementation, its first implementation is so simple. So because it's simple enough, so people could understand it, and everyone could implement their own Kanrens, their own version of miniKanrens, and this is good in one sense, but in another sense, because it's so easy to implement, there are so many different implementations in different languages, and every kind of implementation, more or less, they are a bit different from each other. So my question about this is, since there are so many different implementations and maybe they have different features, so is there some way that different people can communicate, different implementers, they can communicate with each other about those different features in a better way? Because they all extend it in some way, but maybe they all extend the Kanren in different aspects. Yeah. And that's one of my questions. And my second question is about its use. In fact, I'm looking forward to seeing more how people can use miniKanren. We can have powerful interpreters and we can use this to solve some logic problems. But I'm still looking forward to seeing more use of miniKanren. And I'm really curious how people can use them to solve more problems, other problems. And but this is something that I cannot figure out for now. And so speaking of this, speaking of this, so the verse we can see that yesterday, the talk about the verse, it attracted so many people. So but it's also kind of logic program language, and so if and in that in that talk, people they also asked, well, why do we need this verse language? And I think if verse can do that, why we cannot use miniKanren for all of that kind of thing, right? Yeah, that's my question. Yeah.
Okay, thank you. So I had a couple questions there. I was wondering if anyone has answers to some of those questions. I see, Jason's here. Jason is largely to blame for the fact that everyone who's ever used miniKanren has at least one implementation. So, and by the way, I see that kind of as an offspring of the scheme heritage, where my friend Aziz said that he thinks Scheme is the most implemented language of all time because everyone who learns Scheme ends up implementing Scheme at least once. I mean, I've implemented Scheme probably hundreds of times at this point, and so that's sort of the tragedy and beauty of Scheme is that there are literally many thousands of implementations. At the same time, there are only a few implementations that have all the bells and whistles and the engineering and so forth. There may be maybe 5 to 10 really actively maintained implementations. So that, I guess, that might be one way you could look at miniKanren in the future, is that there'll always be a microKanren where you could implement it in an afternoon and really understand what's going on and hack it. But at the same time, we probably need bigger systems. Probably the biggest systems that have existed so far would be core.logic and Clojure, and also maybe cKanren. Claire Alvis at one point had been building out cKanren with a whole bunch of different constraint solvers and so forth. I think it's a real challenge to integrate all of the different logics and solvers and techniques within a single implementation. I also think it'd be worth trying. But I'm curious if anyone else has thoughts on this issue of proliferation of implementations and so forth. Come on up if you have a thought. Okay, please introduce yourself and please keep the mic near your.
Okay. Hi everyone, Xiangyu again from Arizona State University. So quick answer to the question about why we have so many different languages, right? PHP is the best language in the world. That's a simple answer. But if we go into a complicated situation, it's like, okay, different people may have different beliefs, understandings, aspects. That's why we create a diversity in the world. So basically just like a gene in your body, the mutation, if we allow like the varieties of the different things out there, we give it more chance. Like some gene may be mutated into some like very good variations. Then people will start like, okay, look into that implementation, take some ideas. That's why like Java, right? Taking the lambda calculus finally after 70 years. So simple answer is like PHP is the best language in the world because people are always arguing about like, okay, this is my approach, mine is the best, you are bad, kind of this. So this is one thing. And the other thing is like from the Bible, like also like in human world, we have different languages, right? If we all of us speaking the same languages, we build a tower, go to the sky. So that's probably another reason why we have different implementation. We cannot unify into one thing because otherwise we just conquer the world. So yeah, just my thoughts popping in my mind. So it's good, like Will mentioned. Maybe in the future, one system has absorbed into like more and more things. We improve the expressiveness because the ultimate goal is like, okay, the fully declarative, right? Go to bake a cookie and the computer will do the rest for you. You figure out the recipe, what's the flavor you like most, what's the temperature, and then just start executing, serve the cookies. That's our ultimate dream. But currently, I believe we can only slavery some people to do that. That's the best AI out of the world. Like, okay, there's a human being right next to you. So, yeah, hopefully this is our big dream, right? That's why we have a workshop. We gather together. We want to extend the system, add more expressness into there, improve performance, and maybe 100 years ago later, the AI will say, okay, this is one of my ancestors built me. Yeah. We're moving toward that direction.
Thank you. Anyone else have a thought on pros or cons of having many implementations? Or, I guess I could turn around and say, what should we do, either as community or individual implementers in the future, or researchers? Should that be a major direction of research in the future? Trying to combine all these different techniques into one. Dimitri had talked about in an earlier talk about having one Uber system or giant system that had everything in it. Is that something that really needs to happen, and maybe we could coordinate a whole bunch of people to try to make that happen? Or do you think it's better that, at this point at least, people just kind of experiment on whatever they find interesting, and maybe someday the pieces come together, but if they don't, it's kind of, that's fine. Maybe it's more like an idea language. Come on up.
I'm Walter Schulze from, well, let's say Go miniKanren. And I think, yeah, it would be nice to have a Uber fast, optimized miniKanren, right? But there is still value in the miniKanren that's implemented in all these languages. So if we start thinking about very senior engineers, right? And we also think about junior engineers learning how to program in verse. And how they're going to come from verse with all these logic programming constraints to more mainstream languages and go like, what the fuck? Why can't I just do a equalo disjunction existo fresh variable here? Like, and it's going to be hard for the senior engineer to really understand what they're, because they have not had any exposure to logic programming. But if by learning miniKanren in their own language that they're familiar with, they can bridge the gap between this junior engineer who's come from logic programming being second nature to them like having to learn something new after 30 years of programming. So, yeah.
Thank you. So you're suggesting that after people learn verse, they'll move to a mainstream language like miniKanren. I think that's a good idea. I actually do hope that it's possible to sort of piggyback onto the verse train, and so we can have, kind of ride the coattails of, Epic and Fortnite, all those Fortnite skins and downloads and DLC and stuff. We can piggyback somehow on that infrastructure. Well, we'll see. It'd be cool to be able to compile to verse, for example, compile miniKanren to verse if that'd be possible. Or maybe this would be similar to, what Kate was showing, where do mode analyses and whatever. There may be large subsets of miniKanren. In fact, I think there are. I've been talking to verse people quite a bit to try to understand better the design and the future of it. I think there are large chunks of the types of programs that we have written where, at least in certain modes, you could compile directly to verse or verse calculus. And, hopefully they'll end up with, a top-notch, really efficient implementation. So that might be a compilation target. That might be worth exploring, sort of like what the WAM did for Prolog and the JVM for a bunch of languages. Maybe, you can look at verse as, sort of a compilation target. That might be neat. Okay. Any other thoughts on where we should go implementation-wise, or the size of implementation, the complexity, or any of these other things? What was the second question? I got fixated on the first question. Oh, okay. What are other uses? Yeah. Okay. So this is one that comes up perennially. It's like, okay, this is cute. What are you going to use it for? And so you can use it for different things. You can use, miniKanren for learning how to implement miniKanren. Okay, so that's a great use case. You can use the tried and true, sort of like the great thing about functional programming languages is you can use them to implement a compiler for a functional programming language, right? We're, maybe like that, except times 10 for miniKanren in a way. You use miniKanren to write an interpreter for scheme in miniKanren that then you can implement miniKanren in. That's actually my goal. So those are the sorts of things that maybe even worse than sort of the functional programming curse. But it's certainly the case at this point that people have made a lot of money using miniKanren, or at least the core logic version. The amount of money they've made is secret, but I suspect it's on the order of $1 billion. Whether or not that was the right language for them to use, well, they used it and sold a startup well. So people have made money, but it was always in the context of something very pragmatic, core logic, and had sort of relational things in it, but they could always get out of kind of the core language. This is true, dbKanren for megaKanren. That is not 100% pure, and it's also more restricted in ways, more like a data log in some sense. So, I think there are lots of uses of more restricted languages, or where you have an escape hatch and you don't have to be 100% logical. Maybe that's one reason that the miniKanren family has had some success, is that if you're embedded, then you can always escape to the host language. And then, if you look at the optimizations Greg added to Barlaman, he's escaping to Scheme and doing all sorts of things there that you wouldn't otherwise be able to get away with. So the fact that we're embedded in a host language in almost all implementations might be a great benefit in a way. And I think this is maybe one thing that's held back Prolog more recently, is that Prolog's not a particularly popular language these days, and you can write web servers in Prolog, but most people probably would want a web server in another language and then do the logic-y stuff in sort of a subset. So I think that's a sweet spot for miniKanren. But I am curious what people think about other sort of use cases or the direction that miniKanren research and development should go. Should we try to be more pragmatic? This is a thing that came up in the Scheme community as well. Right, so there were things like R4 RS Scheme standard that very much wasn't a pragmatic thing, and then R5 became a little more pragmatic. R6 arguably became more pragmatic because there was a much bigger spec and more libraries now. You actually had libraries for the first time, and then R7 large is trying to do that even more. But at the same time, the success of Scheme is partly because there's a tiny core language anyone can implement and understand. So it's got all sorts of teaching, educational aspect. There's also, it's a hacker's dream. You can hack on Scheme implementations all day long. And you can also, hopefully do programming, more sophisticated programming in large and commercial uses. There certainly have been uses of those. But it's hard to have the same language satisfy all the different users, right? And so miniKanren, I think, has a little bit of that issue. There's educational uses. There are things like, microKanren, like, hey, here's 50 lines of code. And then there are things like faster miniKanren or cKanren, which are much larger and more complicated. And then there's the, well, forget the whole relational thing. Let's just be pragmatic, like core logic, where you add a lot of features that are more like Prolog extra logical features. And so those do feel like different things to me. And so maybe that is the reason that we should keep different implementations and not, if we're going to have an Uber implementation, maybe we have an Uber research implementation. Maybe we have an Uber pragmatic implementation. I don't know. Anyway, thoughts? Come on up. Please introduce yourself and keep the mic near your mouth.
Hi, Lisa Zhang, University of Toronto. This might go in the opposite direction that you're trying to lead us, Will, but this might also relate to some of the earlier questions. I'm just curious about what your thoughts, Jason, other folks in the room, what your thoughts on what exactly is a Kanren, and and whether there is agreement in the community about what constitutes a Kanren.
My name was called, so I get 60 seconds to respond. Jason Heeman, Seton Hall University. Let me try and throw out what I got on both of those in order. What direction should the miniKanren community go? What are we adding of value to other communities? And then maybe what makes a Kanren in my view lately. I think one of the big benefits that we've got is a really nice sandbox to play in. It's a nice sweet spot of an implementation that you can hack on and get really good performance out of. That's not to say that all implementations are eminently hackable or that you get really good performance out of every one of them, but there's a nice spectrum of if you've got an idea and want to see how it works, or if you need just a little bit of logic programming for stitching together whatever other thing you're working on. This is a good repository of knowledge and a community that knows how to get some of those things done. As I'm thinking about what people are interested in doing in the LLM space, I've seen a couple papers now recently on, man, it's sure great to have constraint logic programming available to help either explain or describe what's going on with my LLM answers. So I think some of it is having a group of people and a place to play. Some of the things that where do we go next would be, I think, making sure we keep a clean sandbox. That the things that we know how to do, that somewhere that's organized and archived and made available. Will had talked a while ago about, I guess, a series of like tech reports for here are the things we know how to do in miniKanren. Here are the things that we don't know how to do and don't quite work. And I think having that kind of repository available for, you've got an n-dimensional matrix, here's as many of the spots as we've explored, would be a good thing to have, so that when the next idea strikes and the next person wants to come and grab it off the shelf and do something with it, it's easy and eminently available, as opposed to being difficult to hack on in other spots. What it is that makes a Kanren particular, my answer has been an interleaving depth-first search and symbolic constraints. Our style of symbolic constraints. That's not to say nobody else gets to be a Kanren. Another answer is whatever the people in this room are working on implementing. There's a sociological or historical answer, but if you wanted my answer to scope out the core of the technology, that's what it would be.
Thank you. I guess my take on what a Kanren is, it's somewhat ill-defined, but miniKanren originally started as a teaching language for students at Indiana University who knew Scheme. And so that's why the syntax looks like it does. That's why fresh looks like let. That's why cond looks like cond, things like that. So there is, for good or for bad, kind of this baggage of sort of a tradition of where things came from. I think another thing that makes a Kanren isn't so much the syntax, but it's more this idea that we're going to try to simplify the language to focus on purely relational constructs. So if you look at the first edition of the Reason Schemer, there were two versions of cond. There was cond and condi. Condi was the interleaving version. There were two versions of equal. There was equal without the occurs check, which was the default, and equal with the occurs check. There was all and all I, so interleaving conjunction and non-interleaving conjunction, which meant that any person who is writing a program with a disjunction, a conjunction, and a unification had 8 different ways of writing their program, and it was a mess. And so over time, we simplified things, made it more general, and we defaulted to the more general operation. So we always use the occurs check for unification, even though it's more expensive. We always do the interleaving search, even though it can be more expensive. And so now it's sort of like going back the other way. We went general, and now we're trying to think, okay, where are cases we can be more efficient? Maybe we can use a depth first search in some places. Maybe we can get rid of the occurs check, but we defaulted to the safe and general approach, which is the opposite of how Prolog did it. Prolog was much more about performance, which makes sense from a language from the 70s. And it was also much more about controlling the search, which makes sense given the AI context, the search-based AI context in which it was created. So we made different choices. So the way I see it is every once in a while I'll meet an experienced Prolog programmer who will look at miniKanren, look what we can do, and say, you know, you can do that in Prolog. There's nothing new. You can do it in Prolog. And that is true. However, by the time you're done making it work in Prolog, you've basically turned Prolog into miniKanren, you know, to do those sorts of things. And the fact that we tend to give real emphasis to the relational aspect of things. So even if you do use a conde or condu, the way we teach things, that is sort of the exception to the rule normally. That's the sort of thing that you would avoid. If you really had to, maybe you would use one every once in a while. The Prolog people try to avoid cut often, but for us, we have a much stricter notion of what we consider a non-logical thing. So we, you know, anything like copy term or projection or things like that, we also consider non-relational because it inhibits the ability to run backwards. So I think we're much stricter. We have a much stricter way of looking at things, sort of like, you know, someone approaching scheme from a functional standpoint has a different view of how you use the language than someone approaching scheme from this is a multi-paradigm language and I'll use, you know, mutation and, you know, whatever. So it's just a different point of view. Okay. All right, we got another. Oh, okay. All right, we have a question online from Evan. Okay. All right, I'll give my computer 1 second to wake up. Otherwise, I will ask someone else to read the question. Anyone have the question I can share? Okay, come on out. Oh, here we go. Okay. All right, here's Evan. Evan said 9 minutes ago. Sorry, Evan. My 2 cents is that it would be interesting to try to discuss how complete a miniKanren one could assemble from the various improvements made to individual implementations. The ability to hack specialized versions of MK is a great strength, but I frequently find myself wishing whichever implementation I'm using had features from some other implementation, and my own work has trended towards trying to create a more featureful implementation, which has driven some sometimes very interesting developments. I'd be interested in having a conversation about what a megaKanren would look like at the very least. Okay. Moreover, my experience so far has been that sometimes you reach a phase shift and the more complete version is actually as simple or simpler than the simple version, which sort of happened with this constraint system talk. Okay, Evan's referring to his last talk on using goals as constraints in miniKanren. And I think Evan's right. And I'll give you an example is if you have something like nominal unification for nominal logic programming, which we borrowed in Alpha Kanren from Alpha Prolog, or you can also look at Alpha ML. So if you look at that sort of system, that gives you capture avoiding substitution and other things that are useful. And if you don't have that sort of unification in your system, well, then good luck implementing some of those things. You're going to have to do all sorts of encoding tricks or De Bruyne notation or something like that. And it gets really tricky to encode certain things. So sometimes having a more complicated system, sort of makes your life easier overall. And certainly one of the Achilles heels we've had with miniKanren is You want to do program synthesis via a relational scheme interpreter, no problem. You want to add 1 and 2, have a seat. We need to have a discussion, right? That's kind of the way it's worked out. And we have implementations of finite domain solvers and arithmetic systems of various types and delay goals and all sorts of things like that, and constraint solvers and calling out to SMT solvers and everything you can imagine, but they're all in disparate versions, and none of them are in faster miniKanren, which is the implementation most people are using, at least in the scheme community for research, or in oKanren. As far as I know, none of those features are in oKanren either. So the two big research implementations don't have any of those special bells and whistles. Okay, so I agree with Evan that it would be nice to have, nice to be able to write an interpreter that could do addition. That'd be awesome. Okay, and especially if you want to do something like probabilistic logic programming, that becomes important. Okay, other thoughts? Or what would a megaKanren? Okay, okay. Here's Evan's question: what would a megaKanren look like? What would we want in a megaKanren? I know some people here have opinions because we've talked a little bit about, bigger systems. So don't be shy, please. Yeah. Oh, yeah. Okay, here we go. Walter said, wouldn't it be kiloKanren? It wouldn't be because we don't have a milliKanren. Okay. Okay, well, nanoKanren, exaKanren. What would an exaKanren look like? One of my friends is building a supercomputer, RISC-V supercomputer with 1 million cores on it that fits in a single rack. And so I want to run miniKanren on that. So what would we do if we had 1 million cores and ran what was that? GigaKanren, yeah. Sounds like something Elon Musk would do. Yeah. Okay. Well, what would you want to have in a megaKanren? What would that look like, and how would you go about doing it? Like the SMT people have kind of figured out how to combine theories, so that's maybe something we could copy off of. Okay, but are there other approaches or other things you could think of that you would find useful, either from a research standpoint or a pragmatic standpoint, in a megaKanren? While you think about it, I'll tell you what I'm thinking. I think I've already said I really want a system where, first of all, we have a modular design. We actually have modules, right? So that's one problem with miniKanren right now. So most of the implementation, at least the scheme versions, we don't really sort of modularize things well. But I want to be able to do things like in Chow Prolog, where you can have different searches for different predicates or different relations. So I want this to be depth first search, or I want this to be breadth first search, or this is ID DFS search, or whatever. Okay, so you should be able to parameterize things by search. Right now, we don't have a way of doing that other than going in and hacking a low-level way. So that's an area where we're lacking modularity. And sometimes you can get away with the depth first search because something's finite, and you really should take advantage of that. Another thing is having different logics. Olin Shiver says always use the most, always use the simplest language you can get away with, or the most restrictive language you can get away with. So if we can do something in data log, we shouldn't be using full miniKanren. If we can do something in answer set programming, we should be doing that. So there's no reason to go to full miniKanren for everything because it's very hard to reason about. We don't have termination guarantees or complexity class guarantees, things like that. Another problem we have is we're not doing environment trimming. So as soon as you shove something into the substitution, it never goes out again. Okay, so we don't have the equivalent of garbage collection inside of a substitution. That's an issue. Another issue is, from an implementation standpoint, I think we could probably make another try at getting away from triangular substitutions, which are nice in a way, but union fine has advantages, and composing substitutions has advantages. I think that's something worth exploring, and different representations. Another problem is we only have really one data structure in the scheme version of miniKanren, which is the pair. So we have atoms and we have pairs. And while pairs are very useful, we don't have vectors. In fact, vectors are usually reserved to represent logic variables. And we don't have records and things like that. We don't have sets. Okay, I would love to have sets. There have been times where I tried implementing like parts of TAPL, and then immediately I needed sets. And so I could try to represent sets as lists, but there are all sorts of issues with that. Also, constraints, various types of constraints. I would like to be able to say in this part of my program, I want to have nominal logic constraints, and nominal unification. This part of my program, I want to have finite domain constraints. This part of my program, I want to call out to an SMT solver. This part of my program, whatever. Another thing, speaking of solvers, is it'd be really great if we could incorporate SAT and SMT solver techniques within miniKanren implementations right now. So Nada Min and Michael Ballantyne and other people have done a lot of work trying to get miniKanren to call out to SMT solvers. And we can get it to work, but there's this huge impedance mismatch based on the type of the search and other issues. And you have to call out to this external process. And also, SAT and SMT solvers like it when they have all the constraints up front and they solve them all at once. But that's not how we do things with miniKanren search. Instead, we're incrementally solving things, and we hope to cut off the search space so we don't have to keep going down. And we can also handle recursion nicely, whereas SAT and SMT solvers, you sort of have to unroll things generally. So if we could implement those techniques inside of miniKanren search, I think that would be great. And also there are techniques like back jumping. But if we had conflict-directed clause learning and unit propagation and all those sorts of things in a high-quality, high-speed miniKanren implementation that supported other data structures and other constraints and were modular and had things like data log subsets and answer set programming subsets and all that, that would be a very sophisticated system, especially if it integrated well with the host language, Scheme or OCaml or Haskell or whatever it is. I think that would be a language that would both be a very good research vehicle and also a pragmatic vehicle for people who are doing declarative programming and constraint solving. I think that would be nice. And so we could look at things like Zinc. We could look at things like Flora 2. There's a whole bunch of systems we could look at and draw inspiration from. So to me, that is what I would like to see in a megaKanren. Anyone else have a vision of what they would like to see in a megaKanren? You must have an idea, Jason.
My vision is much more narrow than Will's. I'm Jason again. Will's vision, to me, sounded kind of like Kanren the conductor. There's the Kanren up there, and now you SMT some stuff, now you answer set some stuff, now you stable model some stuff. I guess my vision of it was maybe slightly different. I was thinking of the Kanren being the shop that you go pick stuff off the shelf out of, and if I choose to combine these sorts of theories with this kind of search with that sort of domain, I happen to know what kind of properties that we get out of it as a result. So you go down the shelf, I'd like one of those, or yeah, like a Subway or something. I like one of those, one of those, one of those, one of those, and then they ring you up, and at the end you know exactly what kind of properties you get out of a system. And yeah, the miniKanren App Store. Yeah, that's what my gigaKanren does. Greg, are we just calling people out the audience now, Greg?
Okay. All right. Well, maybe we'll hear more about megaKanrens later. Well, I'll throw out another question. Who has tried using some variant of miniKanren in Anger for a real production system? Not writing quines or generating append, but to actually get work done. Okay, I know there's someone else in the back who's not raising his hand, but okay. If anyone's willing to share their experience, now, I guess part of it's also tangled up in, if you're using it in Racket, say, it may be hard to separate your view of using Racket versus miniKanren and so forth. But, if anyone has views of that, I will say that as part of this biomedical data translator project, we have been using DBKanren, like on the 5th generation of DBKanren or something like that, written in Racket. And so it's sort of a loosely inspired by miniKanren and inspired by Datalog graph database, where you can write data, sort of Datalog-ish queries and so forth. And we've been using that for precision medicine, for case reviews and things like that, and tooling. And it works. It has some nice trade-offs in that, once again, it's something that's hackable. And it's, we didn't have to use, or we chose not to use things like Neo4j. There are other graph databases out there. We didn't use RDF databases and so forth. We rolled our own. And I guess that's one nice thing about something like Kanren or miniKanren is that, you can sort of riff on it and go in different directions. That's not a problem. I know that there was someone who wrote for his PhD thesis in naval architecture, used a version of miniKanren, I think, in Python for a constraint, sort of as a front end for constraint solving, that kind of thing. One thing you could imagine for the SMT solving is like, miniKanren sort of is a front end for SMT solvers. That's similar, I guess, to Rosette in a way. So Rosette's kind of this Racket DSL that's a front end for solvers. So you can imagine miniKanren being used that way. But in any case, if anyone's willing to share their perspectives, that's fine. If you're being mic shy, that's also fine. Oh, okay. All right. Lisa's going to ask a dumb question. Oh, okay. So you're trying to understand Jason's analogy is the App Store versus the conductor model. Okay, so I can tell you what I don't agree with Jason that I have the conductor model of megaKanren. Okay. Okay. So to me the conductor version means there's this giant megaKanren that's in charge of everything and it delegates things. I'm talking more like the programmer is choosing, or maybe through a static analysis, or maybe some lightweight annotations or things like that, there's some way of specifying this relation really is data loggy, or this relation really can, or these sets of relations, or this module really fits into ASP. And so it's more like we have a bunch of different implementations of miniKanren. We have sort of the fully general one, which is actually the one you never want to use if possible. And then you have the highly specialized ones that are much more restrictive that you hope your problem will fit into. It's sort of like if you had a problem that really is truly regular expressions, you don't want to use Java, raw Java. You want to actually use like a regular expression library because, if you convert, this to DFAs or whatever, there's all this great theory about complexity classes and which operations you can perform and termination and so forth that you don't get from general Java programming. You can compile it to be really efficient and so forth, and you can reason about memory usage and so forth. And similar with Datalog, similarly with answer set programming or whatever. So if you have a special class, or maybe you have a subset that's SQL-like, okay? If you know that parts of your program can be very restricted, when parts of your program can use depth-first search and things like that, it's more like either the programmer decides to implement things using those subsets, or the system can maybe prove that certain subsets can be used. Or, like with Datalog, you have syntactic restrictions, okay? And then having that within a whole system. So it's not like this big miniKanren deciding, you do this and you do that. It's more like you have a system that is composed of different logic languages, and but they work together in such a way you can write an application that has 7 different logics in it, 7 different fragments of logics, and they all work together okay, and you have different searches in different places, and it all just works, and it's not a problem. That's what I'm thinking. So I wouldn't, I guess I don't think as a conductor, I think it's more like you have a whole bunch of different DSLs that integrate well together. But as far as the App Store model, I'll give that to Jason to explain.
This isn't worth standing up for. I'm going to stop taking the mic. I tried another way. I guess my vision was a whole lot of options to produce a homogeneous language rather than the kind of heterogeneity that Will was describing, I think. All right, somebody who hasn't talked for a while. Katia? As a prologuer, maybe can I get some outside thoughts? If you please. Sure.
I'm Katya Komendanskaya, and I'm in Britain, in two universities now, in the north and in the south. So I inherited Watt and Southampton. Well, I'm not quite prologue either, so I do logic for computer science. When I was listening to you, I was thinking, because I know logic and I like logic programming, relational kind of stuff, I go to different communities that do relational programming one way or another. I examined the thesis by Dale Miller, and so there's obviously LP recently coming out of Lambda Prolog. There is Prolog itself, but I'm mainly thinking, when I think about Kanren, I think about it in relation to languages like Lambda Prolog. So I kind of separate out Prolog, which is clearly first order, and let it compete with SMT solvers, with languages that try to be logic functional, have Lambda on top of relational reasoning. So LP seemed like an exercise until they worked out that it's extremely useful for SS Reflect and for building up hierarchies. And now it's suddenly, there's a big French community of Coq people, and those who build all those nice libraries suddenly say, oh, great, so LP is useful. So this is one way for such a language to go, is to say, okay, there's a niche for me. This is something that no Prolog, no SMT solver can do, because you have libraries in Coq and you need both relational and higher order. And then you find this sweet spot, and I think this is how, for example, LP is going to work, right? So there's no Lambda Prolog. No, I don't know anyone who's using Lambda Prolog for everyday work. But they found a niche, and this is one way for these languages to survive. And this is actually, this metaverse is the same story, right? They found some kind of cool application, and then they're going to say, well, here's what it is. So you want to have like big labels, so this is where it's cool, and then use this as a reason to develop the language. And miniKanren is different, because it's not trying to say I'm the language for this. It's trying to be a language so on its own. And I think that's how this conversation comes. How do we survive as just a language? Whereas generally these languages of this kind are struggling to survive on their own. But SMT solvers made it, right? So there's genuine need for languages like this. And I'll tell you maybe a different story. So this tutorial that was running parallel to you, unfortunately, on neural net verification. We were thinking what to do with neural net verification. The SMT languages are very bad for talking about neural nets, because neural nets are functions and you want to have good abstractions, vectors, etc. So my team ended up implementing in Haskell a DSL to reason about neural nets. And then we ship queries to SMT solving, well, to specialized SMT solver for neural nets. And there is so little that actually you can do if your high order DSL links to SMT solver. You restrict yourself a great deal, because so many queries cannot be handled. You cannot nest quantifiers like this. You cannot have nonlinear expressions, because they cannot do nonlinear real arithmetic, etc. So there is definitely, for example, for projects like this, for applied projects, there is a niche. I think if there was a stronger solver, maybe more high order solver, or people ask like, oh, if you've proven this for this region and then you have a higher region, maybe you could prove that you don't need to reprove everything, because you could just compare regions. There are clearly some kind of high order problems that could be automated by something that is stronger than SMT solver, or more abstract than SMT solver. And that's again we're lacking this kind of languages. SMT solvers want their niche, and we have functional programming, but there is, as someone who's trying to apply these languages in practice, you often see instances when you want some kind of language in the middle. It's just we don't really have them as freely available as an SMT solver to connect to. So take encouragement from this. You are needed. I think it's maybe for us, for all of us, is to find better ways to persuade people that there is something that we offer that's unique, that SMT solvers cannot do, that Prolog cannot do. And that's why I mentioned LP at the start, because they found something, it's nice to have a few use cases when they say, well, no, you can't do this with SMT solving. You need a little bit of a higher order stuff to do more. So LP, yeah, that's the ELPI. Yeah, it's a dialect of Lambda Prolog. There was Lambda Prolog implemented. ELPI. It's yeah. I don't think they themselves implemented this, but they had a very bright student who re-implemented Lambda Prolog, ELPI, and then moreover went and said, I will also use this to help Coq with connecting mathematical hierarchies, which suddenly said, oh wow, you certainly couldn't do it with a SMT solver because it's too low level. And so such use cases really lift. But LP is easier. It's just language that's only used there. And you're much bigger than LP. And but you're not as used, say, as SMT solvers. And so finding more users, if you like, being a bit more public, or maybe find a few very cool use cases will help you. Yeah. Yeah, they improved high order pattern matching, and yeah. So it's absolutely clear for me that such languages are needed because they get reinvented. There's ELPI, Lambda Prolog, this now Metaverse. They get reinvented because there will be problems that cannot be done with crunching things like in SMT solving. But it's just your problem is that you're trying to survive. There are so many similar languages that are just for this application, for this use case, and you want to be a language that just lives its own life. I think that's where difficulty is much easier to survive as just a niche, one niche language for something, and then to be like 17-year-old language that wants to live 20 more years, or not 200 more years. What's your ambition? Yeah. No, go for some cool project. I don't know, like large language models or something.
So I'm Jeff, and I work with Will and Greg, and so I've been thinking a lot lately about what is scheme, and what different people say scheme is, because I think it's a thing that you can't get by going to one source and saying like, what do you think this thing is? I was talking with Andy Keep last night about what he thinks scheme is, and I think what I see people do is I see people mean there's two. It's like a thing that if you had to write a dictionary definition, you have to at least have two definitions. And definition number one is the thing that is trying to be described in the standard, or that the standard is trying to approximate, right, over successive RNRS. But there's this second, and I'm not saying there's only two, because there's a bunch of different things. Certainly in the top few, there's another definition of scheme, which is it's a physical incarnation of the lambda calculus, right? It's a generally accepted set of encodings of lambda calculus and lambda calculus-like extensions, and that's what people often mean when they say scheme. Like I refer, for example, to the Lambda Ultimate Recursive Knowledge, I think, talk from yesterday or the day before, right? Like they called the thing scheme, but you look at what they're doing and it's like, no, we're generalizing the capabilities of zero knowledge proofs with lambda calculus. and we're going to call this thing scheme, but it's sort of a misnomer. It's like, well, it depends on what you mean by that. So I think for what is a microKanren, like that to me is like sort of this kernel minimal thing, right? And where I feel like the places to answer Will's question about like, have you used miniKanren in anger? Yes, totally. And where that happens for me, my personal sharing that I can work is like, Greg is trying really hard to make his little corner of megaKanren like corner, and I feel like I want like the kiloKanren version of that, of like if I could just escape this like n times k joining thing for getting my biomedical data through with some stupid hacks, right? Like I'm willing to accept stupid hacks. Like I have a paper that I'm going to present tomorrow that's sort of like I would file under stupid hacks in some sense, and it's like I'm willing to accept a lot of like less fancy things if I have some knowledge about like the data that's flowing through stuff, and I'm willing to, if I can't have a query optimizer, that's okay. Like I'm willing to sort of do some busy work to guide that search. And if what I have to do is just like fight with really big constant factors, it makes it feel sort of like a self-defeating proposition. Like if you just don't know what's in the data at all, and you're trying to like get your query to run, and then table scanning, like is like I remember trying to figure out what was in a certain database and table scanning and figuring out that like, the table scanning speed was so much slower than just like writing manual code. Then it's like, okay, it's hard to break down the problem. And so I guess like I look forward to, okay, Moore's law is over, where the hardware going forward the next 30 years is not going to look like the hardware going backward 30 years. And like, when we have the million core machine that strangely has only two terabytes of RAM, right? Like that seems like a small number, right? So like, how are we going to pack things into that machine? And in that space, I feel like there's opportunities for finding big wins on some space of problems. And like, to me, it's not about, I don't know that there is like the one ring to rule them all flavor of megaKanren. Like we can certainly build very ambitious versions. I don't know that like even among the concerns that have like already been explored, like putting them all into one thing is really like, I don't know what that would look like, or if that, I don't even know. I guess I would assume that that's like a non-goal. It was my sort of general sense is it's not one, there's not only one dimension, there's many dimensions, and we know how some of them recombine and not so much others. So, I don't know. End of my stream of consciousness.
Thank you. A couple real quick thoughts. One is, it is true that we aren't a specialized language with a specialized application. So Prolog was kind of this big language. I mean, it is this big language trying to be general purpose. Lisp, is trying to be general purpose. In the functional programming community, I think we accept that at this point, functional programming, can be used for all sorts of computation. And it may be like the FIP stuff yesterday, where it's like in place updates, and we may have to use lots of engineering tricks to make the functional programming efficient enough or to do low level enough things. But we accept that we can do, in general, systems programming and functional programming and things like that. With logic programming, other than Prolog, I don't know of any language, maybe with the exception of Mercury, where you can do general programming, systems programming, and things like that. There are things like Curry, which are functional logic languages that maybe are closer. I don't actually see miniKanren right now as a functional logic language. I think we're just a logic language embedded in a functional context, and you can kind of go between them. Maybe if we had a better integration of the functional aspects, if we did more like Curry or Verse or things like that, then we'd have a language that's more pragmatic and that you could actually use for sort of systems programming. Alan Kay once said that, he made fun of Prolog because he said, "What good is a language that you can't write an operating system in?" And that hurt. I was like, "Oh," I took that personally. But he also said that there are languages like concurrent Prolog that you can use for systems programming. And fifth generation computing project, they had KL1, this kernel language that they could use. They wrote an operating system in it, and they had custom hardware and all those sorts of things. So there may be variants that we can explore that would be interesting. My hope is that even if we have special use cases, which I think we should look for, my hope is that we don't only end up being this sort of niche language that has one application, be it relational interpreter, be it use as a proof assistant or whatever, that we do keep also exploring, in addition to specialized applications, kind of getting to the goal that someday you actually could do things like systems programming. Maybe you have to modify the language, maybe you have to extend it. There are at least two ways of going about programming languages research. One is starting with this tiny, tiny core that you can be efficient. You have a very particular problem in mind that you're trying to solve. You can optimize it and reason about it easily, and that can work really well. And then the other approach is say, hey, we're going to try to swallow the whole world, and if it's a new or relatively new or maybe underdeveloped paradigm, that can be really hard. And I remember when the Haskell people hadn't figured out how to incorporate monads. It's like, oh, great language. How do you do input, output again? Things like that, right? And I feel like we're definitely in that pre-monad stage where we're trying to be a general language, but we just have no idea how to do a large variety of things that in traditional languages just people don't even think about. It's like, oh yeah, why are you even talking about this problem? It's not really a problem normally. So we're definitely in that domain. Another thought I had was there are languages like Lambda Prolog and 12 that look almost like sort of the relational programming languages that we want to use. Also, Coq kind of feels like this way, but like in Lambda Prolog, the Lambda Prolog book, if you read it, there's a interpreter written as a relation. And when I remember reading it, it's like, oh yes, great, this is awesome. And now they're going to run it backwards. Now they're going to do program synthesis. It's like, no, they didn't do anything. Why? Because they didn't have a search. They didn't have the constraints that they needed. So they got all the way up to doing it, but then they kind of either lack the secret sauce or lack the motivation to do so, or both, right? And so that's another thing I think is worth exploring. Nada Min has figured out how to generate quines in 12, for example. Okay, so 12 is a fine relational language in many ways. It's just lacking the sort of search we have, and maybe lacking some of the constraints. So that might be an interesting thing to go back and revisit some of these systems that are almost exactly what you would hope for from a relational system, but for whatever reason, they didn't implement some of the things that we've found over the years to be really useful if you want to do, say, synthesis. And maybe there's a sweet spot there. Maybe we could hack 12. Maybe we could hack, Lambda Prolog or whatever, or Lambda Kanren. Maybe Lambda Kanren already supports this better than Lambda Prolog, but really try to push those angles as well. And then for Jeff, one thought that I had when Jeff was talking is, I've heard several people say this in the past, that relational programming, one thing that is interesting about it is it seems like it's a pretty good glue paradigm for tying together different types of computation, certainly for data things, because you have SQL, flat files, graph databases, data log. There's a whole bunch of different things that you have to deal with if you're, say, dealing with semantic web and traditional SQL databases and modern graph databases and whatever, like we have to deal with on the biomedical data translator project, where we have all sorts of different biomedical data in a whole bunch of different formats. And right now what people do is they take all the data and they say, we're going to pick one format and one representation, and we'll shove it into that format or representation, whether or not that's sort of the natural way it should exist. Whereas I think in the sort of relational setting, at least with like a megaKanren or kiloKanren, we might be able to come up with something that has less of an impedance mismatch, where maybe we combine different types of relations with different degrees of power and so forth, and maybe keep more of the data in its original format, and we lose less of the kind of structure as we try to do the computation across different data bases or knowledge bases of different types. Okay. Let me look online. Okay, I think we're good there. Any other thoughts? Anyone who hasn't spoken who would like to share their ideas? Okay. It's time. Greg's going to come up finally. He's been marshaling his thoughts.
Hi, I'm Greg Rosenblatt. I work with Will at University of Alabama at Birmingham. I have some thoughts about, I guess, the role of miniKanren in terms of pragmatic use cases. So, I think that the right way, this is the way that I think about it at least. I think of miniKanren in as sort of like two different components that work well together. So the part that I like most about miniKanren is as Jason mentioned, the hackability, and as Will mentioned, that it's really good glue. So I like the idea of miniKanren as a sort of central shared language in which you can describe lots of things. So basically, you can make statements of first-order logic in it, right? And I like the declarative aspect of that. What I don't necessarily like so much is the default search strategies of basic implementations. They're very good for lots of. Jason, you're very amused. Okay, so they're very good for toy problems and for doing basic relational interpreter queries like finding clients. The basic interleaving search is very good for that. But in order to really put it to more practical use, you need to go beyond that. So I know Jeff was mentioning, for instance, the join order problem. That's not going to be solved automatically by the interleaving search. You need to build in a smarter system that can look at your constraints and say, okay, this is the right way to schedule them. This is what you were describing as this would be a query optimizer, right? And so that's the second aspect of miniKanren, which is the operational semantics part. So we have the first part, which is a nice syntax for describing things that lots of different kinds of second semantic operational semantics kinds of things can share. So and as Will was talking about, you could potentially have many kinds of operational semantics depending on the exact structure of your problem. So some kinds of descriptions would be good to solve with like data log. Maybe you can write an efficient data log solver that can solve that portion, and maybe you have a more general backwards chaining semantics that leads down to that. So you might have backwards chaining up until a certain point where you see, okay, at the leaves of this search, we see a bunch of things that look like data log, and we'll apply a data log solver then. And so you want something more like an operational semantics that can change or adapt depending on what the current state of your search looks like. And in order to do this, I guess this is something that Lisa and I worked on a few years ago, which was a first order representation for the program, and which I saw Evan Donahue actually in his paper. He mentioned that he was building off of a first order representation as well. You can think of this as a defunctionalized representation of the search. So instead of using a higher order representation of of conjunctions and disjunctions, the M plus and the bind, or is it append infinity and whatever terminology you use now. I like the M plus and bind. Anyway, instead of the higher order versions of those where you're locking a specific operational semantics in the form of scheme lambdas, you instead just say, okay, this is a disjunction or this is a conjunction, and you have a separate interpreter that can then inspect a program, and depending on how your interpreter is implemented, it can dispatch in different ways. So for instance, I was reading in Evan's paper that he actually uses multiple kinds of interpreters, which is really neat. So he has the main interpreter that does a normal kind of interleaving miniKanren search over the program. But then for his lazy constraints, he actually uses a completely different interpreter that interprets disjunctions in a different way. I think that was the main distinction, so that he can achieve his laziness, and as well as figuring out what variables to attribute his lazy constraints to that are currently suspended. So that's I think the example of something that the direction that we want to go in. So these kinds of different ways to interpret the same program structure. So we can build utilities that sort of do the simple things for the common kinds of program structure that is shared amongst lots of programs. So things like conjunctions and disjunctions and existential quantification, and off of these use different kinds of interpreters as like extensions that we can plug in at various points and say, I want to actually override the operational semantics at this point when I recognize this pattern, or some other way to hook into it and say, I actually want to apply a different semantics now because I think that's going to be more effective. And when I say that things could be more effective, just based on my experience, I'm talking like billions of times more effective. And like even in Evan's paper, he was quoting performance, I believe, compared to the normal faster miniKanren implementation of things like disequality constraints. If you do something more specialized for a certain kind of pattern, you get gazillions of orders of magnitude improvements. It's ridiculous. And in miniKanren logic programming in general, when you're splitting the state of the world over and over and over and over again, little tiny improvements in overhead due to being slightly less stupid about basic patterns has enormous, you can gain enormous amounts by just eliminating little bits of unnecessary work at various points. And the only way you can really do this is to apply programmer domain knowledge based on specific patterns. So for instance, just another I guess anecdote for the relational interpreter that we did with Barlaman. Most of those optimizations came just from being a little bit, not even a lot, just a little bit less stupid about the order in which we applied constraints. So, for instance, as something as simple as knowing that a variable, when I say variable, I mean a lexical variable in scheme that's being interpreted by our interpreter, knowing that piece of syntax is ground, it's a symbol, and our environment is ground, we might as well just look it up in the environment immediately and get that value rather than going through the normal miniKanren search, which will continuously delay the search through that environment one binding at a time. That alone gets a large speed up, but even more so, doing something like function application, where you could evaluate the operator or the operands first, and which one you do has enormous consequences for how quickly you're going to be able to run your program forwards or backwards. So being able to inspect the current state, say, is the operator ground, are the operands ground, and based on that status, choose which one you try first. That's the difference between synthesizing a pen from scratch and sitting there for all of eternity and nothing happens. So yeah. So I guess my point is we want to do more of I guess a mix of homogeneity and heterogeneity, but depends on which perspective you're looking at miniKanren from. So program representation-wise, homogeneity is great because we can all share a common language, but from a solver's point of view, we want a lot of heterogeneity. We want lots of different approaches to solving constraints. Best if it's informed by a programmer's domain knowledge. And I don't know a perfect way to express that in a program. Our solutions so far have been kind of ad hoc. You write an interpreter or multiple kinds of interpreters that interpret that language. So I don't know the nicest way to present this to a programmer who's programming in a possible megaKanren or a kiloKanren or whatever. I don't know what that will look like, but I just know that you will need some way for the programmer to be able to describe these things in the future, and I think that's the direction that we should be going in. So, a secret third interpreter in Evan's implementation? Sorry, that does what? Prints debug traces. Okay, yeah, that's a great idea too. So I guess sort of related to that, Lisa and I did a neural miniKanren implementation once. That I guess was the thing that led to our first order representation implementation, which is where we can actually have some external agent in the loop, where you presented the current state of a miniKanren program, and it makes a choice about what. So the agent itself implements the search strategy. It says, I want to go down this branch. Let's try that. And then the miniKanren portion of it takes the choice, takes that step, and says, okay, here's the new state of the program. What do you want to do now? Or it'll say, unsatisfiable, try something else. And like Evan says, you could potentially do something similar to get you debug traces. I think that's also sort of related, where you can do these kinds of arbitrary introspections onto the program state. I think that's a great idea too. I'd love to see what Evan's implementation looks like, and hope I hope that's not secret in the GitHub repo that he presented, because I want to take a look at that. But yeah, so going beyond debug traces, debug interaction is also possible. I guess that was my point. So where you can have a programmer that actually interacts with the miniKanren system. Yeah, I guess another thing we were working on was a miniKanren profiler, which also uses that idea as well, where you can actually inspect the state of the program, as well as track. I guess this is another kind of tracing. You can track the contributions to your current state. By contributions, I mean the program points that have led you up to where you are, and by doing so, you can actually see which parts of the program are most implicated in successes or failures of different threads of the search. And by doing this and generating a heat map of your program, you can actually get an idea of how you might want to rewrite it. We might be able to write other kinds of interpreters that, on the fly, are doing using this for some kind of profile guided optimization style restructuring of the program on the fly. So you can imagine another agent that is watching this. They're consuming this heat map and saying, okay, let me reinterpret these parts of the program in this way and interleave the search in a different way, so that we can avoid all these this waterfall of failures, and hope to get more relevant answers coming through that rather than a generate and test pattern that might be happening at the moment. All right, have I spoken enough? Does anyone else want to speak? Oh, great. All right, I ate it all up. Okay.
Good job, Greg. That's exactly what we were hoping for. Okay. Well, once more, I will plug the monthly miniKanren seminar online that Kate runs. And so if you're interested in joining us for that, please let me know. Or let Kate know. And we're always looking for speakers willing to share their hacking and research and things like that in relational programming or miniKanren or whatever. Thank you to everyone who attended in person and online. Thank you to the student volunteers, and thank you to the program committee, and thank you. Thank you to Nada Min, my co-host, who did a lot of the legwork, and I hope that we can continue meeting in person. It's great to be back in person again, talking about these things, and I hope we'll find great applications, and we'll play around with megaKanrens and nanoKanrens and attoKanrens and exaKanrens and everything else. That would be great. All right. Thank you very much.